Hello everyone, myself Prasad. Today I am here with the new topic, or you can say a problem. So it is on the design of rectangular combined reinforced concrete footing. So it is all about how we are going to design about the rectangular combined RC footing. So here's you can take an example of the problem. So in the problem, from the problem you can say it's a rectangular combined RC footing design. So first let us go through the problem. So, design of combined rectangular RC footing for two columns A and B carrying loads of 500 kN and 700 kN respectively. Where the column A is 300 mm by 300 mm and column B is 400 by 400 mm. And the center to center spacing of the column is 3.4 meter apart. The shape bearing capacity of the soil can be taken as 150 kilonewton per meter square. So here they have stated to use the M20 grade concrete and Fe415 grade steel. So here we are also going to draw the sectional elevation, plan of bottom reinforcement, plan of top reinforcement, and a cross section of combined footing. So from the questions we can write that the given data like the size of column A, size of column B, and what are the load axial load acting on it on the column A and the column B. Also the center to center spacing of the column and also the length between the column and the soil bearing capacity that is 150 kilonewton per meter square. So uh, we'll be calculating, we'll be designing this footing in different steps. So in the first steps, we are going to get the size of footing or the footing slab dimensions, we can say. So the first of all, we are going to calculate the loads. So the total load on the both column will be 500 plus 700, that is 1200 kilonewton. And we can take the self weight of the footing that we will assume as the 10% of the total column load. So we are having 1200 as a total column load and 10% is 120. So the total transmitted load to the soil will be 1320 kilonewton. So as we are having the SBC, that is say bearing capacity of the soil, so soil bearing capacity of the soil, so from that we can calculate the area, as we know that area is equals to total load by SBC of the soil. So from here we can get the area required. So that is 8.8 meters square. Now we'll calculate the footing size and area of the footing provided. So whatever we have calculated now is the area required. Now what we are going to find is the how much area is to be provided. So let us assume that the width of the footing will be 2 meter. So the length will be area by B. Here we'll be getting 4.4 meter. So let us say it as a 4.5 meter. Now sizing of the footing will be 4.5 meter by 2 meter. So the area of the footing provided will be 4.5 into 2, that is 9 meter square, which is greater than 8.8 meter square. So hence it is okay. So the next step is the projection of footing. So let us assume that the projection P1 and P2 should be in such that the center of gravity of footing coincides with the center of gravity of the column loads. The distance x bar of the center of gravity of the column loads from the center of column A will be given by. So in this figure we can see that here we have given the 2 meter as the width and 4.5 meter as the length of the whole footing, and each column is having their own dimensions, that is 300 by 300 and 400 by 400. So from there, p1 plus x bar is equals to L by 2. So from the formula, we'll get the point column A x bar as equals to 0, and point A will be 500 kilo Newton. Similarly, at point column B, x2 will be L, which will be equals to 3.4 meter, PB is equals to 700 kilonewton. So here the x bar will be 1.98, so we will be considering as 2 meter. So here the P1 will be P1 plus x bar will be equal to L by 2. So from here we will be getting the P1 as a 0.25 meter. So P1 plus L plus P2 will be getting the total L. So from here we will be getting P2 as 0.85 meter. Now the next step is net upward pressure intensity on the footing. So net upward pressure, that is Q, will be total column load by area provided. So it will be getting 133.34 kilonewton, which is greater than the soil bearing capacity of the soil. So hence it is safe. The next step is the calculation of bending moment and shear force. So we'll be calculating with the diagram. So for the calculation of shear force of SF at the left of A, that is that will be 66.67. At the right of A will be 433.33. At the right of B will be 226.67. At the left of the B will be 473.33. So SF will be 0 at the distance of x from A, where the bending moment will be maximum. So now then we'll be calculating the bending moment. So bending moment is nothing but the distance into the load into the perpendicular distance. So using the formula, we'll be calculating the bending moment also. Then we will be plotting that in the diagram as in the before one, as we have seen in the before slide. Now the next step is calculation of depth of the footing. So here we will be calculating the effective depth for to resist the bending moment. So using the formula mu by 0.13 at FCKB. So here the effective depth that we'll be getting is 305.62. So we'll be taking it as 310 mm. Now we'll be checking for punching shear or two-way shear. So with the depth calculated, that is 310 mm, uh, for which the critical section of the plan lies at the distance of d by 2, that is 155 mm, around the column B. So here we will be considering the column B because it is having the bigger column cross section. So, so from here we'll be getting the punching factor shear force, and that is since it is factor shear, we will be multiplying it by 1.5. After calculating, it will be calculating the nominal shear stress, the tau v. After that, we will be calculating the permissible shear force, shear stress, and with the from the we'll getting those formulas from the IS 456 2000 class 31.6.3.1, and with the help of those formula, we'll be getting the tau c, tau v, you know. So here what we have found that the depth found from bending compression is adequate. So assume 60 mm effective cover. So the overall depth will be effective depth plus the cover. So the total depth will be 370. Now this means 2V is greater than K2C. So hence the depth is inadequate or insufficient. So we will be revising the required depth. Now the next is design for bending tension in a longitudinal direction or design of longitudinal reinforcement. So here we will be getting the moment. Now for that moment, how much steel is required, that and all we are going to calculate. So the same formula we are going to use the formula from the code book IS 456 2000. Uh, so after using the formula, we are going to get the area of steel that is required. So the area of steel that is required, what we have got is 5687.55 mm square. So we will be assuming 16 mm dia bars, and using the 16 mm dia bars, what is the spacing? So the spacing will be it is 70.7 mm. So we can assume or take it as a 70 mm. So hence we will be providing 16 mm dia bar at 70 mm center to center over top face. Uh, Now we will be going for the sagging portion of the bending, for sagging bending moment. That is the down portion of the bottom face. So here also similarly we are going to use the same formula, and we are going to get the area of steel here also. So here we have got is 112.10 mm square. So the minimum area of the steel, that is 0.12% of the gross area. So the minimum ST will be 888 mm square, which is greater than the 112.10 mm square. Hence, we'll be using the minimum area of steel. Now we'll be assuming 12 mm dia bars. So the after using 12 mm dia bars, the area of steel that we will be utilizing is 113.9.09 mm square. Now for that 12 mm dia bars, we will be calculating the spacing. So the spacing what we have got is 254.7. So we'll be taking it as 250 mm. So providing 12 mm dia bars at 250 mm center to center at the bottom face. The next is check for one-way shear. So we will take the critical section at the column B because it is having a longer column, higher load and higher dimension. So we'll be taking the factor shear force. Then we will be calculating the nominal shear stress. Then after getting the nominal shear stress, we'll be calculating the percentage of steel at the portion A as seen in the figure. Now from there we will calculate the value of tau C, and we will see the permissible shear stress. Since the tau C is greater than tau B, hence the shear reinforcement is not required. So we can provide the minimum shear reinforcement. In the next BV, uh, we will be calculating the percentage of steel. Here again we will be calculating tau C, and here since the tau C is greater than tau B, shear reinforcement here also is not required. So for the minimum shear reinforcement, we will be just assuming 8 mm dia bar, that is 8 leg vertical stirrups. So area of stirrups will be calculated. Then spacing of stirrups will be calculated. Then the next step is the design of transverse reinforcement. The footing will be bent transversely near each column face. For column A, cantilever projection beyond the face of column A, that is B is equals to 300 mm and D is equals to 300 mm. From here we'll be calculating the width of bending strip, net upward pressure, the maximum bending moment that will occur at the face of the column. Then we'll be checking for the depth of footing. Since the depth provided earlier is sufficient, so we'll be keeping the same depth. So we are not going to change any depth. Now the next is area of steel calculation. So again we'll be using that whatever area of the steel we have provided, it is sufficient to uphold the loads or not. So again we will be calculating the area of steel using the same formula, and here we will be assuming 12 mm dia bars, and the spacing will be calculating the spacing. Now for column B, so again we will be getting the net upward pressure, width of bending stirrups, maximum bending moment that will occur at the face of the column, and then we will be checking for the depth, and after the checking we will be calculating the area whatever we are going to provide in the column B. So it is similar to the column A. Now what we have to provide the minimum reinforcement for the remaining portion. Like we calculated for the portion till portion A, column A, and portion till column B. Now in the middle remaining portion, we will be providing the minimum reinforcement. So here we will be providing the minimum reinforcement with the spacing. And the next step is the reinforcement details. Now we'll be looking towards the details in the reinforcement, how it is distributed, how it is shown. So we can see the upper bar is the 16 mm dia bars at 70 mm center to center over top face, and the 12 mm dia bars at 300 mm center to center at the bottom face. So and in the section A to A, the so in the verticals 8 mm of 8 leg vertical stirrups at 175 mm center to center has been used at the near the column, and in the middle 8 mm dia of 8 legged vertical stirrups at 200 mm center to center is used. So here the depth of the total depth of the footing is 370 mm, while the effective depth is 310 mm. So this is the sectional elevation. Now looking towards the cross sectional of combined footing, there is 16 mm dia bars at 70 mm center to center over top face, while 12 mm dia bars at 250 mm center to center at the bottom face. Now looking towards the plan of bottom reinforcement, so the distribution bar is 12 mm dia bars at 300 mm center to center bottom face for the width of 2560 mm, and the main reinforcement of 12 mm dia bars at the rate 70 mm center to center for the width of 920 mm. Again for the next 12 mm dia bars at 60 mm center to center for the width of 1020 mm from column B towards the column B, while in the middle or the lower reinforcement we have provided 12 mm dia bars at 250 mm center to center. So now the next we can see the plan showing top reinforcement. So this is how the top reinforcement looks. So the distribution of the main, you can say it is 16 mm dia bars at 70 mm center to center over top face.